So a triple integral is going to arise from the same kind of Riemann sum logic that double integrals and single integrals arise from. So once again, we're going to skip over the Riemann sum formalism of where triple integrals come from, and just observe that a triple integral of a function of three variables can be computed, just like double integrals, using an iterated integral. And the integral with respect to one variable, and then we integrate with respect to another variable, and then we integrate that with respect to the third variable. So we integrate from the inside to the outside. So one of the differences with triple integrals is that if we're using even just rectangular coordinates on xyz space, if I have constant bounds on one of my coordinates, like let's say I choose x ranges from -2 to +3, as in the setup of this first part of the activity that we're going to do. Setting x equal to a constant in xy space gives us a vertical line, but in xyz space it gives us a vertical plane. Right? So bounding x between -2 and +3 is telling us that our x variable is going to be trapped in between these two parallel planes in xyz space. The plane x equals -2, which is the one on the left there, and the plane x equals +3, it's the one on the right. Then if I bound my other variables, if I bound my y's, for example, between 1 and 4, as we have in this problem, that's going to bound with two more vertical planes, y equals 1 and y equals 4. So my y variable is going to be bounded in between those two vertical planes. So now I've sort of trapped myself into this box over here. And then I can bound my z variable, which is going to give me kind of a top and a bottom for my box. And in the activity we're going to do, that's z equals 0 and z equals 2. And so the bottom of my box ends up being the xy plane, z equals 0, and the top of my box is at z equals 2. And so what it gives me are these 6 planes that together sort of define 6 sides of a rectangular prism that is going to form my domain of integration. So in rectangular coordinates on 3 space, if all of our limits of integration are constants, then we are integrating over a rectangular prism region, right? A box, basically. And so if we want to integrate over something that's not a box, we're going to have to go and use that tape measurement process of bounding a variable in between functions of the other variables, and then squashing that variable out and bounding one of those variables in terms of the other, and then squashing that out and getting constant bounds for the third one. But just to get our feet wet, the first thing that we want to do, just to get the practice, is to find the integral of the scalar function x minus y plus 2z, where the region of integration is that solid box, x ranging from -2 to 3, y ranging from 1 to 4, and z ranging from 0 to 2. Let's take a few minutes and work out that iterated triple integral. So setting up our first iterated triple integral wasn't that bad. We were integrating this function x minus y plus 2z over this rectangular box, x ranging -2 to 3, y from 1 to 4, z from 0 to 2. So one of the first questions that came up in your discussion was, which order should we integrate this in? With respect to z and then x and then y, or x and then z and then y, or, well, we have 3 different coordinates to choose from, and any ordering of those coordinates is in principle a possible way to integrate. And there's 3 factorial, or 6 different orderings of 3 elements. So there's 6 different orders that we could choose to evaluate this integral. Fortunately, here, since our bounds are just constant, we can reverse those orders however we want to without having to go back and re-tape measure our region, right? So whichever way we want to do this, we'll come out with the same answer. So just reading the limits of integration from alphabetical order from left to right is a totally valid way, which lets us do the z integral first, and the y integral second, and the x integral last. And it turns out that this integral ends up equaling 0. And so if this function x minus y plus 2z is kind of seen as the density of space inside of this box, it's not a very good density function because it's negative in some places and it's positive in other places. But this kind of means that this function is exactly as negative inside of that rectangular box as it is positive inside of that rectangular box. It spends as much time and energy being negative inside of that box as it spends being positive. And so when we integrate it over the box, everything cancels out to 0. Right, so the bounds are constant, order of integration doesn't matter. So to trouble that concept, we'll go forward to part B, where instead of a box, we want a region that is a solid cone inside of three-dimensional space. And so the bottom side of this cone, the sort of the part that the ice cream would sit on top of here, right, would be given by this cone graph formula, z equals square root of x squared plus y squared. And the top of the cone is the horizontal plane z equals 3. So the solid region that we're talking about is all of the space inside of this cone. So the cone-shaped part is on the bottom, and then the horizontal plane is here on the top. And so it's all the space in between. And so the trickiest part, as it always is just figuring out how to tape measure this region so that we can get limits on this integral. So again, we have these 6 different orders that we could try, right? We could try to tape measure the x-coordinate first, and then the z, and then the y, etc., etc. So we just have to find one that's going to be the easiest on us. And in this example, I think starting with the z-coordinate makes the most sense. And the reason that that makes the most sense is that we already understand the bottom side of this solid region, the lower bound on this region, as z equals a function of x and y. And also the top side of this solid region is also z equals some function of x and y, right? It doesn't have an x and a y in it, but you get my drift. So because the bottom and the top of my cone are already defined by z equals something, tape measuring the z-coordinate first is probably the best idea. So you sort of stick a tape measure here into the cone and say, what's the top side? It's z equals 3. What's the bottom? It's this cone, which has equation z equals square root of x squared plus y squared. And that's going to give me an inequality that bounds the z-coordinate. Then the next step would be to take and squash this cone so that the z-coordinate is gone. In other words, squash it onto the xy plane, project it onto the xy plane. And that projection looks like the figure on the left here. It looks like that disk of radius 3 centered at the origin. Then we have to tape measure that to get us bounds on x and y, and that's exactly the kind of tape measuring that we did, in double integration. So our task for the next few minutes is just to get this triple integral set up that would be capable of finding the total mass of this cone if the density function is given by some arbitrary function delta of x, y, z. So we'll do the tape measuring, and then after that we'll talk a little bit about how we might evaluate such an integral without having to work too hard. So we set up this triple integral over this solid cone, starting by bounding z in between functions of x and y, because that's the most convenient way to understand the bottom side and the top side of this cone. The bottom side is the cone z equals square root of x squared plus y squared, and the top side of the cone is the horizontal plane z equals 3. And so bounding z in between square root of x squared plus y squared and 3, and squashing the z variable out of this solid region, it makes a grease spot on the xy plane in the shape of the disk of radius 3, centered at the origin. So then we have to tape measure that disk in the xy plane, which if we choose to do that as a type 1 region, we will end up getting exactly the same tape measurement as we got a little earlier today when we were tape measuring circles, disks of radius r. Here the role of r would be played by 3, and so the type 1 description would be y equals minus the square root of 9 minus x squared to y equals positive the square root of 9 minus x squared. And after that, we squish out the y variable so that we only get the grease spot of that on the x-axis, and that ranges from x equals minus r to x equals r. In this case, again, the role of r is being played by 3. So those are our bounds, and that means if we're going to set up a triple integral dz, dy, dx, then this is what that triple integral would look like as an iterated integral for whatever density function delta goes into that spot. So now if we want to actually evaluate this integral, starting with the z evaluation, then we would need to know what is a formula for the function delta. So what density function are we actually trying to work with here? And so just for this problem, I chose the density function x plus z. So if what we're trying to do is find the triple integral of the function x plus z over these bounds, so x equals minus 3 to 3, y goes from minus the square root of 9 minus x squared to positive the square root of 9 minus x squared, and z goes from the square root of x squared plus y squared to 3, and our integrand is x plus z, and we're integrating dz, dy, dx. Whoops. What doesn't it like here? I think it doesn't like this. There we are. All right, so there is our iterated, sorry, I got to scroll that a little bit. There is our iterated triple integral. And so if I'm going to try to evaluate this, I'll start with the z integral. And then we're going to take a pause after that step. So the antiderivative of x plus z with respect to z is going to be xz plus half z squared. And then we're going to end up needing to evaluate that from z equals square root of x squared plus y squared to z equals 3. Evaluate from z equals square root of x squared plus y squared to z equals 3. And then we need to ultimately integrate that thing, dy dx. So we're going to keep that little piece off to the side here for the moment. And so when I do that evaluation at z equals 3, I get 3x plus 9 halves. And when I do that evaluation at z equals the square root of x squared minus y squared, I get x times the square root of x squared minus y squared plus half of the quantity x squared plus y squared. So this ends up being a little bit nasty. So that, what did I say, 3x plus 9 halves. And then minus x square root of x squared plus y squared plus 1/2 of the quantity x squared plus y squared, because we get z squared and then evaluate that at the square root. Oof. Okay, so let's see. Let me just put this down on the next line here so that we can see the whole thing. So this ends up being what our new integrand looks like. But when it comes time to do the next step in this process, I probably don't, well, I would probably like my life a little bit better if I didn't have to have all these square roots running around in here. And plus, the region in the xy plane that we're integrating over is this disk of radius 3, right? And so converting into polar coordinates is probably in play, right? It's probably a smart move for this problem because my region of integration is a disk in the xy plane, and therefore my limits of integration, if I convert this into polar coordinates, are going to be constant. Also, I have a lot of x squared plus y squareds running around in my integrand, that those are just going to turn into r squareds in the process. So when we do this polar coordinate conversion in polar, if we do a polar coordinate conversion on this, then the integrand, let's just copy this down here. Oops. The integrand is going to turn into 3x is going to be 3r cosine theta. X, again, in front of that radical, is going to turn into an r cosine theta. But then the square root of x squared plus y squared, I'm realizing now you can't quite see what I'm doing, so let me just uncover what I'm doing here for a second. The square root of x squared plus y squared is going to just turn into a single r, which is always a nice thing to get rid of a square root of a sum anytime that we're trying to do integration. And so that just becomes r squared cosine theta right there. And then the x squared plus y squared that I have here in parentheses, that's going to turn into an r squared. And so my new integrand, it still has a little bit of thetas floating around in there, but it's not too bad. And now I just need to change my dy dx. So my rectangular element of area becomes r times dr d theta. Let me make sure I get some parentheses around what matters here so that we don't lose anything in the shuffle. So now I've converted my integrand, I've converted my element of area, I have to convert my limits of integration. And so I have to go back and re-tape measure my region in the xy plane that I'm trying to integrate over. And again, that is a happy re-tape measurement because it turns us from these nasty variable bounds that have square roots in them into nice constant bounds, r ranging from 0 to 3 and theta ranging from 0 to 2 pi. And so when I put those into this integral, my limits of integration turn out a lot nicer. So theta running from 0 to 2 pi, and r running from 0 to 2, or 0 to 3, rather. R dr d theta. There we go. And now I have a polar coordinate integral that is actually pretty doable. And in the interest of time, we won't go through all the rest of those details. But I will flag this example for sort of what we learn in the process along the way. Is we started with a triple integral that was in rectangular coordinates. And so we started out with a volume element in rectangular coordinates that was dx, dy, dz, or whatever order that you like to put those three in, right? And we did the z integral just as it was. And then we took the x's and the y's and we transformed them into polar to get r dr d theta. And so the upshot of this is that we could have called this a cylindrical coordinate volume element. Instead of dx, dy, dz, we could have in the very beginning transformed x and y into r and theta before we even started the integration process and left the z as it is. And if I did that, then my volume element would have turned into r dr d theta. That's what the dx dy would turn into. And then dz just stays as it is. And so if we're doing a triple integral in cylindrical coordinates, we would start by describing everything in cylindrical coordinates, so changing the x's and y's into the polar r and theta, leaving the z as it is, and then replacing the volume element, dx dy dz, with r times dr d theta dz. So that same r that pops up when we make the polar coordinate transformation pops up for exactly the same reason when we make a cylindrical coordinate transformation. And so the last thing that I just want to talk through without really doing an example, I think there's an example or two in the homework if you want to take a crack on it. Let's see. When I post the homework, there'll be an example or two in spherical coordinates, but we're not going to dwell on it for too long. The question that I just sort of want to tackle here is what should happen with dx, dy, dz in the case of a spherical coordinate integral. So remember the spherical coordinate transformation. Is x is rho sine phi cosine theta, y is rho sine phi sine theta, z is rho cosine phi. And so how do we find out what becomes of the dx, dy, dz? Well, it gets multiplied by this Jacobian factor, which I'll just present using the algebra and the calculus here. So the way you find that Jacobian factor is by finding all the partial derivatives of all three of these coordinate functions. So the derivative of the x function with respect to rho and with respect to theta and with respect to phi. Then the derivative of the y function with respect to those three things. Then the derivative of the z function with respect to those three things. And you get this 3x3 matrix that we would call the Jacobian matrix for this coordinate transformation. And the factor that we multiply dx, dy, dz by is the absolute value of the determinant of this 3x3 matrix. So this is a linear algebra creature that we're going to talk about later in the semester if you're in linear algebra. But for us, I'm breezing over it because it's not the point for today. When you take the determinant of this thing, you get a nasty trigonometric expansion that you hit with the Pythagorean identity a couple of times, and it all works out to minus rho squared sine phi, whose absolute value, because phi is between 0 and pi, this is always non-negative, so the absolute value is just rho squared sine phi. And so the upshot is that in spherical coordinates, dx, dy, dz gets replaced by rho squared sine phi times d rho, d theta, d phi. And so if we're converting a rectangular into a spherical coordinate integral, that ends up being the substitution that we make for the dx, dy, dz. And we'll have to transform the integrand in terms of rho, theta, and phi, and tape measure our region using spherical coordinates. So that's the nastiest coordinate system that we'll work with in a class like this, and we're not going to do too much with it. So I don't want to dwell on this for too long. So I'll let you get a little bit of practice with this if you like in the homework. This is one of the those supplementary topics because it is so involved. But yeah, those examples will be there when I upload the rest of the homework problems either this afternoon or tomorrow morning.